All right, today we are working with kind of advanced work with our rational functions. The big tip here is when we're asked to perform operations with rational expressions, simplify early and often. And we want to do that using the factoring skills that we've gotten. In example one, if we're simplifying, we're looking for things to cross off. We want to first simplify this expression as much as we can. Um, and I'm going to do this through factoring. One of the first things I'm going to do is try to factor out everything I got. So on top, it looks like I have an instance where I have a greatest common factor. So I'm going to kind of make a note, GCF of 4. And I'm going to take out that greatest common factor where I can throw that in front of everything and be left over with dividing everything out from the top three terms, x squared plus 3x, because that 12 divided by 4 gets me to 3, and minus 10, because that 40 divided by 4 gives me 10. Then I also have this instance on the bottom here where I have difference of squares, diff of squares. So instead of writing that x squared minus 25, I can write this as x plus 5 times x minus 5. Now, if I look here, there's still nothing I can cross off on top and bottom. So I'm going to kind of look at this blue portion here. I'll throw the blue parentheses around what we have. I'm going to say, okay, this is something that I can factor as a quadratic. So I'm going to multiply two numbers to give me negative 10. And then I'm going to add two numbers to give me positive 3. And if I do that, I think I'd have a positive 5 and a negative 2. Positive 5, negative 2. Yep, that should work. So I can rewrite this factored equation one more time. I get 4 times, I'll replace this in blue here, x plus 5 times x minus 2, and then all of it divided by what we had on bottom already, x plus 5 times x minus 5. And if I work through that, then I can see that there's some stuff to cross out. I can cancel out this x plus 5 on top and this x plus 5 on bottom. And so I'm just left with this 4 times x minus 2 over x minus 5, which I can then simplify out to 4x minus 8 by multiplying over x minus 5. So that's one example with simplifying, and you'll notice that there's a spot on your notes for limitations. We're going to talk about that at the end of example 2. So moving on to example 2, this same kind of process can happen when we are dividing. So first thing I'm going to do before I do my keep, change, flip, I'm going to try to factor this as much as I can. And it looks like the really only spot that I need to factor is this blue portion right here. So I'm going to quickly rewrite it and go with x minus 5. I'll write everything else out divided by x plus 1. And this blue portion here is something that we can, we're going to multiply to negative 5, add up to negative 4. So we'll have negative 5 and 1 should be the combo that gets us there. So on bottom here, I'm going to have x minus 5 times x plus 1. And now before we do anything, I'm going to apply my keep, change, flip so that I can see how everything plays out. So I'm going to keep my first expression, so x minus 5, over x minus 5 times x plus 1. Change my division to multiplication, and then I got x plus 1 divided by x minus 5. Oh, sorry, divided by just x there. My apologies. Almost made a mistake. There's my keep, change, flip. And I like to rewrite this one more time to have everything in one clean fraction, x minus 5 times x plus 1. And we have x minus 5 times x plus 1 times x. You're going to notice there's a lot we can cross off here. The x minus 5's cross off. the x plus 1's cross off, and we're just left with x on the bottom. So our final answer there for that division problem is 1 over x. Now, as we did that, we crossed off a lot of things. And with rational expressions, we need to remember that, hey, we cannot divide by 0. This is a big idea, and I'm going to bold it. I'm going to underline it, at least on my notes here. So if we look back to example 1 and 2, we should list the values that x cannot be equal to, because we took a lot of information away by simplifying it. So if I look at example 1, we basically look at everything we crossed out, or looking at all the factors on the bottom. We have I'll throw a rectangle around it. We have x plus 5 here that's on bottom, and we have x minus 5. So if we're thinking about what values we cannot have x equal to, we can't have x equals -5 or x equals +5. So what we would do is we'd say, hey, x cannot be -5. That's a not equal to sign. X also cannot be +5. Let's just go back, check that one more time, make sure we have that right. Yep, those are my only things that are on the bottom there. So those are the values that x cannot be. If we look at example 2, it looks like on bottom of our initial equation here, we had factored it out where we have we have factors of x minus 5, and we have factors of x plus 1 and factors of x plus 1. Now, notice how I didn't include the top x in the equation. That's because based on the original problem, that could be 0. Well, I guess actually we can't divide by 0 anyway, so we wouldn't be able to divide by 0 there either. Anyways, that's a quick tangent. We have a situation where x cannot be +5 and x cannot be -1, because that would make our denominators 0. So if I go in and write this, we would have a situation where x cannot be +5 and x cannot be -1. All right, lastly, building off of this idea of 0 denominators, this is going to build into how we work with solving equations, specifically in this idea of extraneous solutions. So sometimes as we work through something, we're going to attain values or potential answers that are not actually solutions, okay? So this would be something to potentially bold as well. This not actually solutions, I'm going to bold and underline it in my definition here. And let's kind of see what we're talking about. So in example 3, we're given a problem, x squared minus 25 over 5 minus x equals 12. And some of you might see that we can apply the same idea of factoring to help us simplify this equation out. I'm actually going to kind of wait until the end so we can kind of review how we solved polynomials. But if I work through this, I think that I'm trying to cross multiply to solve these equations. So one thing I'm going to do is I'm going to throw a divided by 1 right there, and then I'm going to go through with my cross multiply. So then I get 1 times x squared minus 25, which is just x squared minus 25, and we get 12, and so equals to 12 times 5 minus x. So let's simplify that out. We get x squared minus 25. We get 60 minus 12x. And then I'm going to, since we have this quadratic, I'm going to move everything over to the left side of the equation. So I'm going to subtract 60 from both sides. I get x squared minus 85. Well, let me throw those lines there to make it easier. Equals negative 12x. And then I'm going to add 12x to both sides to give me, and I'll write this in standard form, x squared plus 12x minus 85 equals 0. We're dealing with a polynomial, so we want to set everything equal to 0, and then we can find the zeros in order to find our solutions. This one's a more difficult one, so for multiplying to this 85, this negative 85 here, and adding up to 12, the combo that would work, let's see, oh geez, that's a bad 8. Adding up to 12, we would get, I think it would be positive 17 and a negative 5, positive 17, and negative 5. So that took me a while to work through on the side here. So don't worry if you didn't see that right away. We'd factor this out. We'd get x plus 17 times x minus 5. And then we're just seeing what values are equal to 0 there. So if we work that through, that would be x equals negative 17 or x equals 5. If we look back to our original equation, though, x squared minus 25 over 5 minus x, we can't have a value of 5, right? So if I'm thinking about checking for extraneous solutions, I look at this equation, x cannot be 5 here, because if we plugged in 5, let's say we did 5 squared minus 25 over 5 minus 5 equals 12, we'd get a situation where we would have 5 squared minus 25 over 0, and we can't divide by 0, right? So that would not work out. X cannot equal 5, so our only solution there, even though we got told x equals 5, our only solution there is x equals negative 17. Now, if you were to graph this, you wouldn't even need to worry about it. This would take care of itself in the graph. Let's check this out. I'm going to throw this as my f of x equals x squared minus 25 over that 5 minus x. And my other function I'm going to throw as that g of x equals 12. Double check, make sure I threw that in correctly. X squared minus 25 over 5 minus x equals 12. Cool. Then I'm looking for my solution. So boom, looks like right off the bat I do have a solution at negative 17. But if I kind of zoom in on the 5, there is no intersection here on my graph. And actually, we'll see that if we highlight in, there's a hole there on my green graph right at 5. So there would be no solution there because 5 cannot exist. And I can zoom out and see, hey, that's even true at those larger numbers.